Kia ora, I'm Troy, HERA's Chief Executive, and welcome to Stirring the Pot. Thanks for connecting. If you're new, here's what you can expect. We're going to be talking the tough stuff, the things that keep us middle minds up at night. There are many challenges facing our industry and equally many opinions on how we should tackle them. Stirring the Pot provides a facilitated forum to discuss and challenge these viewpoints.
So let's get to the nuts and bolts of it. Today we're having a kōrero with Professor Charles Clifton, renowned structural engineer, long-time HERA collaborator and freshly named Fellow of the Royal Society Te Aparangi.
Hello, Charles. Thank you for joining us today. And first of all, I would like to say my congratulations on your achievement of being named Fellow of the Royal Society Te Aparangi. So let's start our question with a bit of your personal background. Can you tell us a bit about yourself and your current work?
Okay. Oh, thank you, Harris, for inviting me, and thank you, HERA, for inviting me. My current work is involving teaching and research into aspects of structural steel and composite steel concrete buildings, increasingly getting involved a bit more in steel frame and engineered timber floor buildings, also some work on light gauge steel, pallet racking systems, increasingly on the fire response of all of those types of buildings under severe fire. So pretty much what I did when I started at HERA, it's just an extending that work into the university and teaching to a large number of students and at undergraduate level and at postgraduate level. Yeah, so it's a natural progression of where I started 40 years ago. There are a few things, for instance, on the durability side that I don't get involved in now that I did when I was at HERA, plus acoustics. I know a bit about vibration of floors, enough to know what to do, but I no longer lead that area of research as I did when I was at HERA.
Yeah, great. Thanks, George. When did that early curiosity for engineering take shape?
Now that goes back a long way. So I was born in 1955 in a remote part of southern Hawke's Bay, and I can remember a lot of my childhood. So I grew up on a farm, which was a fantastic place to grow up, and a couple of things that really perked my curiosity for engineering, admittedly not civil engineering initially. Dad was a very well-known engineer in the New Zealand Army, and also when he retired to the farm, he was involved with the Central Hawke's Bay Electric Power Board. When I was 5 years old, I asked Dad, I was curious what those silver metal strips around power poles were for. And he explained they were to stop possums from crossing the power poles and onto the power lines, because if they did this, there'd be a big bang and flash and a possum would fall to the ground. But then I said, how can birds sit on the power lines? They don't bang and flash and fall onto the ground. And Dad said they only touch one line at a time. So I thought of this possum falling onto the ground really got my imagination going. So Dad had told me a bit about electricity and how it's conducted. So it gave me an idea. I thought, well, if I took a piece of steel which conducts electricity and threw it so that it landed on two power lines at once, I could see what happened to the possums. So after a bit of fiddling around, finding something that was light enough that I could throw up onto a power line, Mum had a lightweight baking tray. So after sitting out there, fortunately very quiet area out on the main road, which saw very little traffic, I threw this thing up, and after many goes, came down, landed nicely on two lines, huge bang and a flash, and a piece of molten metal fell to the ground, and all the power in the area went out. So Dad's, being chairman of the local Central Hawke's Bay Power Board, got quite a few inquiries, and I was somewhat severely reprimanded for that. So another of my forays into engineering was dam building and hydrology. So Dad was putting a culvert over a little local stream, and I was helping him and explaining to me how dams work and how you divert the river and then you block it and watch it rise. So once he'd done, there was a small pipe left over, and I decided to try my hand at dam building. So it's I managed to get the pipe into the middle of the stream with the water flowing through it, and with a shovel and a bucket, it was only a small thing, I managed to build about a 1 metre high dam. Then I blocked this off with a piece of timber and watched the water rise, and when it got near the top, I thought, right, now time to pull this loose and open up the dam. I realised that I'd had to do this quite quickly because the dam wasn't actually as stable as I'd hoped. Then I also found that the water pressure was so great I couldn't move the piece of timber I jammed across the pipe, and it was so muddy I couldn't see it. And the dam collapsed and sent a small wave downstream, but that didn't do much damage. So then I went on to slightly more closer to my final area of research. I had a Mum and Dad gave me a present of the forerunner of Lego. They were a thing called Starlocks, building blocks. You could build little houses and things. And I used to spend many hours building a range of houses and then determining how many flicks of a standardised rubber band it would take to knock them down. So that sort of gave me quite a bit of interest in shapes and sizes and vulnerability to the flicks of a standard rubber band. And that sort of led on since then to full-scale 3-storey steel frame building testing on shaking tables. But, of course, that was a bit later. So, yeah, my early years, I was really inspired to engineering from quite an early time, although I went to University of Canterbury without a clear idea of what I wanted to study at uni. I knew I wanted to be in the South Island. I got a distance allowance because we lived in Taupo, and with that and the A bursary covered all my fees and accommodation at Canterbury, which was really good. My Bachelor of Engineering years were 74 to 77, followed by my Master's in 1978. When I started at Canterbury, we didn't have calculators, and all calculations were done on slide rules. And calculators came in year 2 and would replace slide rules by year 3. I had a lot of fun and loved Christchurch, a fantastic spot. I was fortunate to be taught in reinforced concrete by the late great professors Bob Park and Tom Paulet, who were world-renowned at Canterbury, and Canterbury Engineering School was world-renowned, followed by my Master of Engineering with Peter Moss. And this made me really comfortable with concrete, so I left university with a strong desire to design iconic concrete buildings. In structural steel, I actually gained very little information that was of use. We were mostly shown all the ways in which steel structures had collapsed around the world due to some key component being missing or being under-designed, which didn't exactly inspire a lot of confidence in design of the material. I also, in 1975, while living in a cupboard above the stairs in a flat that contained 3 couples and me, I first met my beloved wife, Linda, and our love story would have got off to a faster start in 1975 if I'd gone to visit her on my Honda 90 step-through in midwinter and was chased away by her landlady with a broom when I first tried to ask her out. But that we then reunited in 1978. So that, I think, covers my early curiosity. So
Nice.
what else?
What were some of the turning points that helped shape your path into structural engineering?
Aha. Okay, so after a stint in Wellington as site engineer and clerk of works on one of the high-rise buildings there, in April 1981, we embarked on our big OE working in the UK. And I had left Canterbury with a strong desire to design iconic reinforced concrete buildings, and I really got my wish. I worked for a joint UK-Saudi Arabian organisation called RH Sandbar Consultants, and I designed the Arab National Bank headquarters and the very spectacular King Saud University entrance gate in Riyadh, which is the Quran and the Book of Knowledge open back-to-back facing each other, with the pages splayed out and with forming an Islamic arch. When you stood at a certain distance away, you had to have a clear shape Islamic arch. So that was the most complicated and the most spectacular building I've actually ever been involved in designing. So then we decided to return to New Zealand in 1983, and I asked Bob Park if there were any university jobs going. And he replied no, but he did recommend me to Gavin Fletcher, who was the director of HERA. And so when we arrived back in May 1983, we were met by Linda's parents at Auckland Airport with a letter from Gavin inviting me to come for an interview at HERA's offices in Auckland about starting the HERA structural division. And my comments were, "Oh, I can't possibly take that job. I'm a reinforced concrete man. And besides, I don't want to live in Auckland." Thus, in June 1983, with a classic New Zealand reinforced concrete university education, I walked into HERA's offices in Friendship House to commence my job as HERA structural engineer. And my job description was to build the technical foundation to grow the market share for steel with a focus on multi-storey buildings. Current market share in those buildings at that stage was effectively 0%. And the exhilaration of having that job was really great. It was a unique job, but tempered by the realisation that nobody used steel and there was no supporting guides, and so there was a big learning curve. And that's one of the things that is so hard to believe, because structural steel is now arguably the most used building construction material in New Zealand. It's hard to imagine how different that was in the beginning of 1983. A massive dispute between the Boilermakers Union, who controlled welding, and the government in the early 1970s had killed off steel frame buildings. The government had issued a decree that no further government buildings were to be built using structural steel. And that had led to, by 1983, the belief that steel wasn't as good in earthquakes as reinforced concrete, unreliable to use outside because it rusts. Unless it's encased in concrete, it would collapse in a severe fire. And besides, even if you could get past all of those hurdles, you'd have industrial relations problems during construction.
Good. Probably you already mentioned about that, but I know that you had a big connection to HERA throughout your career. Can you share a bit about that history?
Yes. There were the three perceptions: no good in earthquake, no good outside, and will collapse in fire. So I had to work hard on determining what parts of those perceptions were realistic, what parts weren't. The bits that weren't, make certain that we presented alternatives and presented realities that overcame those perceptions, and the bits that were, developed new procedures for. So one of the first things was developing seismic design procedures for structural steel systems, because reinforced concrete was now well covered by capacity design, which was the latest thing at the time, controlling buildings to withstand severe earthquakes with controlled damage but remaining intact. And we had to do that for steel. So one of my starting points was back in 1986 to 1990. I was Greg McRae, external supervisor at Canterbury. He and I, between us, developed the capacity design procedure and also the minimum design actions that are required for the members that are protected from yielding until the mechanism is developed. They are designed for the overstrength actions from the elements forming the mechanism. I hope that makes sense to listeners. But the key thing there is to avoid, you generate very large demands in what we call the secondary members. So think of the moment resisting frame. The beams are the primary members, the columns are the secondary members. And if you're not careful, you can build up huge demands in the columns through capacity design. So to make it work economically, you have to have upper limit actions. And Greg's PhD, which looked at MRFs and eccentrically braced frames, came up with some recommended upper limit actions, which were a really clever piece of work. He also did experimental testing and showed of a I-section column, bare steel column, under constant compression load and bending back and forth to form a plastic hinge, and finding that, in fact, as soon as that happens, the plastic hinges shorten a very large amount very quickly. So we had to keep hinging out of columns, even if it wasn't necessary to prevent overall building stability, but because at the end of the earthquake, you'd have some of your columns 100, 200 millimetres shorter than the others, and from a building post-earthquake building repair point of view, that's a pretty disastrous situation to be in. Then that led on to the development of the predecessor to the Steel Structures Analysis Service. So that was started in the Engineering New Zealand, or I-Conference in Nelson in 1994. We seconded Martin Feeney who's with Holmes Consulting to run that. And Martin and I produced the HERA report R476, which gives the seismic design procedures for moment-resisting, eccentrically braced and concentrically braced frames. Now, the really good thing from our point of view is that all of those systems have performed well in severe earthquakes since then, and for which I'm very pleased and proud. When I was on sabbatical in Canada in 2015 with Professor Robert Tremblay at École Polytechnique de Montreal, I asked him why the Canadian steel seismic design provisions had so much in common with the New Zealand provisions. He pointed to that HERA report on the shelf and advised that at the time the first Canadian steel seismic provisions were being developed, our design procedures were the best international guidance available and were widely used. And so we've kept close links up with Canada ever since. Then we went on to the friction sliding connections. Now, in 1994, the Northridge earthquake hit parts of Los Angeles, and the traditional steel-framed building type was a strong column, weak beam, welded, rigid, moment-resisting frame, with the connections partially bolted, partially welded on site. So the idea is that the connections are stronger than the beams and stronger than the columns, so you get your plastic hinging in the beam. It was intended that would be the mode of failure, but in fact, the earthquakes partially failed the beam-to-column connections. Typically, one or both of the flanges broke and left just the web, taking all of the actions between the beam and the column. But despite that, the buildings actually performed very well. I saw that as a significant opportunity to put forward development of semi-rigid connections based on the development of the dependable deformation occurring in the connection. In other words, strong beam, weak connection, strong column, which was completely blue sky and going against all conventional wisdom. Research for that started in 1995, and that led to the flange bolted joint, then the sliding hinge joint, and since then the optimised sliding hinge joint. And the flange bolted joint was used in the Owen Glen building at University of Canterbury, and it was started actually before I'd finished my PhD. So when I was presented with my PhD in 2006, the Vice-Chancellor there, the late Stuart McCutcheon, his comment to me when he put the cap over my head was, "Those joints are better work." And fortunately they do. Then the next thing was the concern over fire. So the fact that if steel buildings, so there is a sort of failure temperature of steel, that if it gets to 550 degrees in fire, it's going to collapse. And so if there's a building made of steel and the elements get to 550 degrees, the building will collapse. But in 1990, there was a severe fire on a steel frame building under construction in London, which subjected 2 stories of uninsulated steelwork to temperatures well in excess of 550, the temperatures up to around 1,000 degrees. Some of the members were damaged, building didn't collapse, damaged members were cut out and the building was restored, which then led to the obvious question, why didn't it collapse? Which led to what is the behaviour of complete steel frame buildings with composite floors and severe fires. The only way to really answer that was to build a full-scale building and try and burn it down. And that's what was done from 1997 to 2003 at the Cardington Large Test Facility in London. And it showed that the floor systems in particular have very high reserve strengths in fire. So from 2000 and onwards, I worked with the principal investigator for those tests. It was Colin Bailey from the UK, and with others, including University of Canterbury brands, to incorporate that reserve strength into a design method called the slab panel method, which is now used extensively in New Zealand, Australia, and also in the USA. I received a recent joint AISI publication from 2023, that describes its application in 4 USA buildings. And that was really encouraging. So up till then, I didn't realise how much it had been used in the UK. Now we turn to the third point of weakness in steel, which is that it rusts. And that has led to the development of an excellent standard for applying protective coatings. That's AS/NZS 2312. But that requires a user to first determine the surface-specific atmospheric corrosivity category for that piece of steel. And that standard gives no useful guidance on doing that at all. So it's pretty much analogous to having a loading standard for earthquake, or having a standard that says you shall design for earthquake, but the loading standard not containing any design spectrum, any soil classification effects, and just saying you've got to design for earthquake, you've got to determine how strong the earthquake's going to be, then you can start the design. So it was one of the things I'd been very keen on ever since starting at HERA, was being able to look at the influences that make up the surface-specific corrosivity category and seeing if I could express all of those mathematically so that we could then develop a mathematically based design procedure to work that value out. And over 20 plus years, I did that. Using experimental testing from Brands in 1981, working with Clark Highland at SCNZ and with NIWA to link all their corrosion data to climatic variables so that we could quantify the macroclimate, and then going round and looking at a whole lot of corrosion sites, house roofs, metal fences, buildings, transmission towers, etc., to build up a mathematical picture of the effects of the microclimate. And the end result of that was HERA Report R4133, New Zealand Steelwork Corrosion and Coatings Guide, published in 2006 by me and by Raed El Saraf, who I'd appointed in 2002 as my junior engineer. And that's the one area that I'm actually in some ways most proud of, because that was unique. Everything else on the seismic and fire side of things we followed on from the work of others and built on it, but that was completely new. It was a New Zealand invention and picked up and adapted by the Australians, so it now forms the basis of their corrosion provisions as well. It was then implemented into a standard because it's quite a moderately complicated publication, and a new TS standard has put that into simplified forms. And a good example of how far that's had influence is the fact that we've increasing use of steel in road bridges, which even 2 decades ago would never have happened because concrete was actually considered and specified as the only durable option for a road bridge. So that covers the big 3.
Thank you, Charles. So, as in my understanding, your work with HERA really transformed how we design a steel structure for seismic and fire events. So why was this work so important?
Because the 3 reasons that when I started, steel had 0 market share was the perceptions of not as good as concrete in earthquake, not suitable outside because of the rusting, and the issue of the 550-degree failure temperature in fire. So the fact that it wasn't as good as concrete in either earthquake, durability, or fire. And because of that, nobody used it. So those were the things that I had to focus on getting answers to. In the transforming, it was to overcome those perceptions that was the main reason for that.
So is there any other misconceptions about structural steel in extreme conditions?
Certainly the perception that steel buildings with composite floors perform well in earthquakes is now well and truly established. That's the performance in Christchurch, in the Christchurch earthquake series, was excellent. And in other recent severe earthquakes, such as the 2016 in Wellington, So I think the earthquake side of things is well and truly covered. The fire side of things is reasonably well covered, but I want to come back and talk a little bit more about that. The outside, the perception, the durability one, I think there is a real need for the industry to develop their certified coatings applicators and to develop quality assurance for coatings on steelwork as they have done for quality of fabrication and now certified steel fastener, supplying of steel fasteners. The steel does rust and people don't like seeing rust spots on steel. There's a much more of an understanding now of what you need to do to prevent a new piece of steel from rusting for a certain period of time and being able to do that reliably. But sometimes the whatever coating system is put on doesn't do the job it's supposed to do, and you will start to see deterioration quicker than people are expecting. And I think that's really important, that perception that steel is not as good as concrete being used outside because it shows rust, whereas concrete doesn't show the effects of ongoing deterioration until you've basically got to pull it down. That is still a disadvantage for steel, and I'd really like to see that certified coatings applicator scheme up and running, because it would address the last perception that I think still has the power to put some people off using steel. Fortunately, not very many.
I see. So after 4 decades, what areas of research or technical focus are you still passionate about today?
Now, okay, more on fire and on developing design procedures for fire that better represent how steel behaves, or design and detailing procedures for fire. So that's one. The second one is the corrosion side, but that's not really me. That's more helping where I can the industry to develop the certified coatings inspectors and to get that side of things now to the point where they've got the quality assurance for fabrication and general fabrication erection and supply of fasteners. The cold form steel area is a fascinating area. It's an interesting material. It's cold form steel houses in Christchurch were built or designed using the same non-specific design criteria as timber-framed houses, but they performed very much better in earthquake. But both systems performed well, especially with lightweight roofs, but typically the steel-framed houses suffered negligible damage, whereas the timber houses suffered quite a bit of cracking of linings and cracking and popping of linings, and so needed extensive repair, and I'm talking of new houses. So like cold form steel framing, it's an incredible material. It's a pain to design, it's complex to design. There's a lot of ways it can go wrong. There's a lot of little details that can make a big difference as to how it performs, but it is starting to be used more in the sort of more than 1 or 2 story buildings. And I think it's got a big future in medium-rise residential construction, which is one of the areas I'm working on at the moment. Also have been involved with one of the big pallet racking companies in New Zealand, looking at enhancing the seismic capacity or seismic resilience of pallet racks. And we've done a lot on that to improve that. In terms of where things are going, now there is the need to look at sustainability and embodied carbon in construction. So that's both looking at you need to build a particular building from new or whether you can modify it, right through to the manufacture of steel from hydrogen. And one of the advantages I had from talking to one of my new fellows at the Royal Society is that they are actually actively working on developing a source of hydrogen that can be used in the rotary kilns of the Glenbrook plant, which is interesting, and it wouldn't be the first in the world, but it would be one of the leaders.
Thank you, Charles. Are there new frontiers or challenges you are excited for the next generation to tackle?
Yes, I think one of those is the making basically a low carbon steel. The other one is the construction for demolition, where you can reuse parts of the building once you've finished. Circular design, that is becoming increasingly more important. Engineered timber is coming, and it does go well with steel. There are some significant technical issues to be overcome for that. One of the things that I'm starting to tinker around with and talk to people who may be in a position to get this implemented is in the building code. We have a requirement that the performance criteria in the mandatory part of the code that gives the 35 general areas of building performance all have to be achieved with a, quote, low probability of failure. But low probability is not defined, and there is now an increasing desire to actually put figures on what is the low probability of failure, so that when building new design and construction systems are being developed, they can be put through a more rigorous reliability determination to determine whether a particular system, say, for example, a steel frame building without passive fire protection but with a sprinkler system with a dual water supply, is that sufficiently reliable to make the probability of a severe fire in the building so low that the consequences are unimportant? And with putting actual performance basis figures in the building code, so in the legal document, would be a major step towards being able to do that. And there are some buildings around, for example, that really would have benefited from that. The International Convention Centre would have benefited from it the first time round, and then the roof caught fire, and I was expert advisor to Fletcher's for the rebuild. And the second time round, they would have had another opportunity to use that to be able to eliminate a lot of the passive fire protection in the building and use the sprinkler controlled fire as the design fire. So some of the changes to the regulatory system would really benefit that.
Right. Thank you. You have recently been named a Fellow of Royal Society Te Aparani. So what does this recognition mean to you personally?
I'm very pleased and proud for that on behalf of both myself and the university and HERA and the industry. It's interesting, when I was at HERA, Wolfgang Schultz, who was director before Troy, said, I would love to nominate you. I would love to be one of your nominators if you wanted to nominate yourself to become a fellow of the Royal Society. And I know a bit about the Royal Society. I knew a bit about it for years. And I said, chances of the Royal Society, who are strongly pure science focused, chances of them being interested in having a fellow from an applied engineering background are pretty much non-existent. So I said, I don't really want to. Anyway, he persuaded me to, so in 2015 I did and wasn't successful. But applications roll over for 5 years. They just automatically come up each year, and you can either just leave them there or update them. So by 2019, I'd actually started to build up quite a bit more of an academic career. So it was something that counted in academic circles, whereas all of my HERA work, even though I started as Associate Professor at University of Auckland, it was discounted in the university system, and I had to really start my academic career from scratch under the university hierarchy. But by that stage, I'd had enough, so I updated the application, put it in, didn't get anywhere, then forgot all about it. And then 2023, Bruce Melville from our department and Andrew Cleland, who had been president of the Royal Society and before that was, I think, president, director, now Engineering New Zealand. He had been working very hard to persuade the Royal Society that they needed to widen their scope of interest in fellows from just the pure sciences and the health and social sciences. And thought I was a very good test case, so I said, no, what's changed? And anyway, they promised to work on me in 2024, and they did. And so I put in a revised application. Andrew and Bruce had a good look over it. And anyway, that went in June, I think, or about then. And I got it. So I was very pleased. And now there's only 2 of us in the Department of Civil and Environmental Engineering who are fellows, myself and Bruce, Melville. And I think there's 4 in the whole faculty of engineering. And it is a big deal. I didn't realise how big a deal it was until I got the information back on what it entailed and what I needed to do, and this event in Wellington that was going to give the conferring of the fellow status on 23 of us. But yeah, I was very proud of it.
Great. What's the one thing you hope people remember about your mahi?
I'd like to hope that they remember the things that have worked and worked well, and the advantages that it's brought to both to HERA, SCNZ, University of Auckland, my family and the country. And I'm hoping that nothing that I have developed actually turns out to be fundamentally wrong in the future. And that's not just a facetious statement. Having been around now for long enough in the system, if you look at Bob Park and Tom Paulet, who were 2 of the giants in concrete, they did excellent work on designing concrete frames, but those frames were supposed to include in situ concrete floors, and in situ concrete floors and in situ concrete frames, extremely earthquake resilient. What happened is that the industry, to speed construction up, changed the in situ concrete floors to precast concrete floors, which have performed very badly in the recent earthquakes and will also perform badly in fire. But that sort of undid a lot of the good work that they did is now not so well remembered because they relate into concrete buildings that had a problem with one of the components that they never actually tested. And in my own area, Igor Popov, who was a professor and became Professor Emeritus in America, he was one of the ones that led the development of the combination web-bolted, flange-welded beam-to-column connections. And he's now not so well remembered in America because he's seen as the developer of the standard rigid moment-resisting frame connections that performed badly in Northridge and needed a lot of repair. So hindsight is a wonderful thing, and I'm hoping that none of my mahi ends up producing something that needs major repair in the future.
Okay. So, and finally, the last question is, what advice would you give to someone starting out?
Okay. I'll say the advice I do give to students starting out: pick the type of engineering that you really do feel keen on doing. Don't go into electrical or something because your parents are electrical engineers but you'd really rather be a civil engineer, or vice versa. Go with a type of engineering that really does excite you and interest you. And then you need perseverance to be successful in your career. I think you need a strong family behind you. Secondly, you need perseverance because you're really in this for the long haul. It's not like your career is over at 40. You're going to be looking at doing this for decades, not years. And you need a strong element of luck. I've known some engineers who are extremely bright ending up crippled with some serious illness and having their whole career cut short. And while I've been at University of Auckland, we buried 2 such people who would have had brilliant careers if they'd lived longer. So there is an element of luck. Also, the other thing that is an element of luck is that our steel frame buildings did perform and have performed and continue to perform extremely well in earthquake, whereas the concrete buildings did not. I would have said roughly a third of that was good luck on our side and bad luck on their side. For example, things like eccentrically braced frames. We design the braces, the bit that force the active link, which is the yielding element, up and down. But to do that, they've got to push the floor slab up and down. We don't take into account the resistance of the floor slab fighting back, but we do realise that it's actually not unsubstantial. But because the braces were strong enough to not yield in compression or buckle in compression, but were able to push the floor slabs up and down, the floor slabs then behaved as an elastic medium and actually helped all the buildings self-centre. Now that was something that we didn't expect, we don't design for. We are starting to a bit more now, but we don't design for that, and yet it worked in our favour. This column shortening, if the column bases yield, if you design a building where the superstructure yields by deformation compatibility the column bases have to yield. In Christchurch, we saw earthquakes where the full mechanism was developed in the superstructure, but we saw no column base yielding. That student, Winston Hay, has just finished his PhD looking at the reasons for that. We're now working with Shahab at AUT, developing design guidance or critically reviewing all of the current design guidance we have. But it showed that we actually did get this pretty much right there without realising it in some cases, and suppressing that plastic shortening at the column bases, which actually would have been quite detrimental to post-earthquake repair. So if you had all your gravity system columns ending up 150, 200 millimetres shorter than all your seismic resisting system columns, you've either got to cut out and replace a lot of columns at the ground floor, or you've got to pull the whole building down to reconstruct. And we haven't had to do that, fortunately. So things like that, there's an element of good luck, and that's really it.
So there you go. Thanks for joining our conversation with Charles today. If you'd like to connect more with him, you'll find his details in the show notes. From backyard experiments to becoming a Fellow of the Royal Society Te Apirangi, Charles's story reminds us that sometimes the most unexpected careers leave the strongest legacy. Food for thought till we see you next time. So hit subscribe, and if you like what you heard today, please like, review or share with any metal minds you know. Let's spread the word. Inspired by Charles's journey? Why not dive deeper into the future of structural steel, fire and seismic resilience by checking out the research we're leading at HERA? You'll find links to some of our mahi in this space in the show notes.